In the Centripetal Force Lab, students will use this apparatus to measure both the centripetal force on a mass that's moving in circular motion, as well as the angular rotation rate of that rotary system. So from that angular rotation rate, measurement of the radius at which the mass is moving in a circle, and a measurement of the mass, the students can compare the centripetal force to their calculated value of m omega squared r. They will do this graphically by plotting data points taken as the mass swings around. And when they compare those two expressions, they expect to see correlation and equality. So we expect to see a slope for the scatter plot that we generate with a slope of 1. Okay, so the experiment itself is pretty straightforward. Plug the sensors into the data logger, displace this about 90 degrees from equilibrium, start recording data, and release. So the bulk of the data the students analyze will come directly from their data logger. The two other things they'll need to know are the mass that's traveling in the circular path and its radius. So to measure the mass, they can simply turn the entire system vertically and then on their data logger read out the weight that the force sensor is measuring, and that'll be the total weight of all the different mounting components, brackets, and the external disc that have been added, all of which are moving in a circular path. So they'll take that weight divided by the acceleration due to gravity to get their mass. Now, in order to find the radius of the circle that mass is moving in, we need to know where the center of mass of all those components are. And that's the part that can be a little bit tricky. We treat it as if there's two different parts. There's an external mass, which is going to be the disk and the two posts symmetrically spaced around the disk. Those two parts, because of their geometrical symmetry, have a center of mass located at the center of the disk. Most of the mass, about probably 95% or so, is located in that part. But there's also some mass that's internal to the force sensor. Primarily this bracket here that connects the external mass into the actual sensor has a mass of about 8 grams. So the students can simply use that accepted value. It's stated in their lab manual. They should not try to remove the external mass in order to measure the internal mass separately. In the past, when we've had students do that, and it typically results in the force sensors getting broken or pieces coming off and getting lost. So do not encourage them to do that. Okay, so they can measure the distance from the rotation axis to the center of the disk, and that will be the radius of the external mass. The internal mass, they're not really able to locate where its center of mass is, but they have an outer bound from where that bracket ends, and they have an inner bound, which is where the force sensor begins. So they can measure those two bounds and use them to describe the average and the uncertainty in the internal mass. And then they can work through the equation for the center of mass of the system, combining the internal and external mass. The equation is actually given in their lab manual, since they haven't covered that in class yet. But from that equation, they can use in series the product quotient rule, then the sum difference rule, and then the product quotient rule again to work out the uncertainty in the center of mass for the entire system.